Is on programming a generic lookup and update function for infinitary inductive recursive types. So that's a lot of words. I'll explain them in a minute. So the motivation is how to write functions over these sort of data types with complex properties, and specifically how to write functions that operate over that not only do something like lookup over such data types, but actually manipulate such data types with something like update. So the properties are dependent arguments. That's maybe not so unique, but more unique is infinitary arguments and induction recursion. And we want to do so generically. So here's sort of a canonical example of an inductive recursive type. We have a universe and its meaning function with natural numbers and pi types, or dependent functions. And this has dependent arguments. You can see the A gets reused, and it has an infinitary argument. So the infinitary argument is a argument to a constructor whose codomain is the type that you're currently defining. So you can see type there is in the codomain. And induction recursion is mutually defining a function with, we're mutually defining a data type with a function that operates over it. So the paper covers all of this stuff. So the functions are lookup and update for specialized data types, and a generic lookup and a generic update for any data type. And with the dependent arguments, infinitary arguments, and induction recursion properties. And for the purposes of this presentation, I'll be talking about specialized update for data types with dependent arguments and infinitary arguments. So the infinitary arguments are higher order, which makes this interesting. A lot of previous work on generic programming restricts your universe to a first order case. And here instead we say, no, let's figure out how to write generic programs, or programs in general that are doing things with higher order data. And the dependencies is a little bit more standard, but a lot of the techniques that you use to handle dependencies extend to induction recursion, because in a sense, all induction recursion is doing is adding a dependency to the constructor arguments that are of the type that you're currently defining. So the strategy that we're going to use is to try to write total versions of functions that would normally be partial, and we're going to make them total by taking advantage of constraints that we can create with dependent types, and something called computational argument types, and something called computational return types. So first of all, I'll explain a quick difference, a little overview of algebraic versus computational types. So algebraic types, here's another mention of vector. So for you guys playing dependent types bingo, mark your cards. Vector can be defined of data type declarations in AGDA like so, and type of finite sets. But we can also, and then we can, of course, define operations that functions that operate over these data types, like a index respecting update. And we can also define these data types, or these type families specifically, as functions where we case analyze the index and create a new type out of existing types. So in this case, a vec of car2 will just unfold to car product unit. And we can then derive the constructors definitionally. And we can do the same thing for like the type of finite sets. So the finite set of 2 will unfold to unit disjoint union bottom. So we can basically select into the first or the second of the units. And again, we can derive its constructors and define functions like update over these computational rather than algebraic data types. And the one caveat is we need to pattern match on the index so that the actual computational data types can unfold, which we didn't have to do in the algebraic version. So that's all kind of review. And here's explaining what computational return and argument types are. So normally we might have a function that's partial, like head, taking list A to A, and we can't write that directly in type theory. So the question is, how can you make it total? Well, one version, maybe sort of the Haskell-y version, is we can add a default argument, like in head 1. So not only do we just take a list A, but we also take an A that we can return if the list is empty, or we can just change the return type to be a maybe. But dependent types allow us to be a little bit more precise in this. So we can create a computational argument type which says, okay, headarg says if the list is empty, then we will ask for an A to update with. But if the list is non-empty, then we'll ask for a unit. Or sorry, if the list is empty, then we can ask for a default argument. And if the list is non-empty, then we can ask for a unit, which is basically not asking for anything. And so it's called computational argument type because the type is used in the argument position. And another version is computational return type. So you can see head 4 has head rep in the return type position. And here head ret will return unit in the empty list case because looking up the head in the empty list shouldn't give you any information, and unit just does not give any information. And in the non-empty list case, an A. So this is kind of how we can use dependent types, specifically computational argument and return types, to turn what would be a partial function into sort of a nice dependently typed total function. And we'll use these techniques later. So as a little warm-up, we'll update natural numbers. So this path data type is just an index into either an entire natural number or the 0 at the bottom or any of the successors going down to the 0. So we can basically point at any subcomponent of a natural number. And with the update function, what we ask for is the natural number and then a path indexing to some subcomponent of the natural number and the natural number to replace that subcomponent with. And if we move on to updating lists, then first we're going to see two versions of updating lists. The first is updating the parametric arguments of a list. So in this case, the path index type in the here case can point to the x, which is the parametric argument of the list. And you can also see in the update function what we're going to take is an a, which is the parametric argument to replace at some position of the list. And in the update function here, you can see if we have a here, then we can look at that y and return the cons, replacing what was in the x position with the y, and then maintain the x's. And if we have a there, then we return cons x, so we keep the previous x and update somewhere in the rest of the list. But we can also write a different version to update lists at the recursive elements instead of the parametric elements. So in this case, the path, the here case, can point to any recursive element. And in the here case of update, we take a list wise to update. And using the technique of, so using the technique of computational argument types, we will now combine these two update functions into a single function. So the idea is this index type, the here constructor points to any recursive position. The there one constructor points to a parametric argument, the x here. And then there two just points somewhere else in the list. So that's what our combined index type becomes. And now we can define our update computational argument type, I think I mentioned, here. So update L is the computational argument type, and you can notice in the here position it asks for a list A. In the there one position it asks for a parametric A, and in there two it keeps on recursing to find what type to ask for. And then update L will, instead of taking an A or a list A, take an update X's I. So the computational argument type is dynamic with respect to the path that's indexing into the list that we would like to update. And then the here case of the update uses the y's that the update has, and the their one case uses the y to replace the cons x with a cons y, and the their two case just recurses and maintains the x that was already there. So now we're going to get to the interesting part. So we're going to talk about updating rows trees. So a rows tree is typically defined like this, right? So we have a constructor called rows, and it has an A for a value at the branch position, and then a list of branches of roses, right? But we're not going to use this. We want to. I want to show an example of writing functions for infinitary types. So we're instead going to define an infinitary rows tree like this. So the first two are these type isomorphisms. So instead of defining a vector A of length n is isomorphic to a function of fin n 2a. So this was kind of mentioned in a previous presentation. It's basically the isomorphism between a vector and its lookup function. And then a list can be defined as sigma natural number and then a vector of length that natural number. So it's sort of using an existential to quantify over a vector of any list. And if we take these two isomorphisms and embed them into the constructor of the rows tree, then we can say, okay, another way to define a rows tree is to take an A, to take any natural number, and then ask for an infinitary function from fin n to a rows A. So this is perhaps an unusual way to define a rows tree using dependent types and infinitary arguments, which is kind of neat, and we will see shortly how to write an update function over such a data type. So first of all, the path, the here case can index directly into the rows, the whole rows. The there one case indexes into the value, the parametric value x. The there two case indexes into the natural number n, and it requires a sort of recursive path into the natural number for what part of the natural number we want to update or point to. And then we have this extra case, this there three, and really, so there three wants to point to the f, but we want to be able to update any position in the infinitary argument. So the index of a type with an infinitary argument has to also be an infinitary argument. And so we have this argument g of type fin n to path applying the fin to the f, which is the infinitary argument of our rows tree. And what this allows us to do is it's a little, the path, the idea of the path data type is no longer just a single path, but it's actually a multi-path if you're talking about an infinitary argument. And the reason why this is important is because you might want to update an entire branching structure of a infinitary argument. And if you imagine the infinitary argument had an infinite domain, like nat to tree or something like that, then if you did not have an infinitary index, you would only be able to, say, update the infinitary argument at point 0 and 1 and 2, but you'd never actually be able to finish infinite updates to across the whole domain of natural numbers. But by making the index type also have an infinitary argument, we can update any, or rather the entire infinitary argument of the rows tree. So this now we're going to need to define the update r, or the computational argument type function, and update mutually. And this slide kind of shows the easy cases with question marks and the difficult cases. So if we're trying to update at here, then what we're going to ask for is a maybe rows A. I'll explain in a moment why it's a maybe instead of just a rows A. And if we're trying to update as at a parametric, then we ask for an A. If we're trying to update at a there too, then we ask for the natural number. And then if we're trying to update at there 3, then we'll get to in a moment what we want to ask for. And when we do the update, For here, then we just use maybe, and when we do the update for there 1, then we replace the rows x with y, and we update rows with there 2. Then we replace the n with update n, and we don't quite know how to replace the f of the there 3 case yet. So we'll take things one at a time. At first, we'll look at we'll do a little bit of interactive sort of programming and see what the goal types are for constructing a definition of updating the there 3 or the infinitary position. So what argument do we want to give in the computational argument for there 3? Well, when we actually perform the update, the infinitary argument that we want to create is a function from fin n to rows a. So what we can ask for is a function from fin n to the rest of the updates. So this is kind of similar to the idea of using an infinitary argument in the index. Well, when we create the computational argument type, we also create this pi type, which is over the entire domain fin n. And then in the there 3 case, once we have this extra argument, which is now in scope as the type h, then we can get our I, because the goal type got a fin n as an argument, and just apply it to all of the functions fi, gi, and hi. Or apply all the functions to I, rather. So then the other case is what to do with this natural number for there 2. And the reason why this one is interesting is because we're going to update a dependent type. Or rather, we're going to update an argument that is used dependently later on in the data type. So for there 2, we want a natural number to update with, but then the goal, once we've updated the number, is going to be because of dependent types, it's going to be an infinitary argument of fin update to rows a, rather than fin n to rows a, which is the thing that was already there, right? And with dependent, what we would sort of like to do is just put f there, because we're like, we have the natural number that we updated, and we don't want to touch the rest of the stuff. And the way that we can accomplish that is we can actually change our computational argument case for there 2 to not just ask for a natural number, but also ask for a forgetful function from finite sets of update to finite sets of n. And once we have that forgetful function in scope, then all we need to do is compose the original infinitary argument f with the forgetful function g that we received from the computational argument type. And here's just putting this all together, all the cases filled in. And visually, we can see how to use this update function with this visual rows tree. And this is just code to show that, yeah, you can encode this in Agda. And here's an example of what we would like to do. So we would like to update this rows tree by removing the f. Okay? And the way that we're going to do that is we're going to say, okay, first of all, at the top level, at the A branch, we're going to say there 3 because we want to update the infinitary argument, because we're trying to get down to f through d. So for the B case, we're going to say we're going to update this entire branch, but use nothing, because nothing represents an identity update. That's why we have a maybe type in the when we were saying maybe rows A, that's why it was maybe rows A instead of just rows A. And for the C case, again, we'll update the entire branch with an identity update. And for the D branch, we'll say, okay, now we want to update the natural number, and we're going to say natural number there too at here. So we're going to update the entire number, and we're going to update it with 1. And then we need to define a forgetful function that goes from finite set of 1 to finite set of 2. And raise1 then is just a Agda standard library function that will allow us to make the fin1 point to the second element in fin2, which will effectively keep the g but remove the f. So this is cool, but one question, and here's just some Agda code that you might want to look back at the slides to verify that what's happening. And what we want, the visual representation is definitely much nicer. And you might ask yourself, what happens if we want to add a node, right? So if we want to, let's say, add a node like H or something, then we would have this problem because we'd have to define a forgetful function. So first of all, we're going to say there2 here and change the branching factor to 3, right? But now we have to define a forgetful function from fin3 to fin2, and that's only going to allow us to point the third element to one of the existing elements. So we could only do an update that would result in FGF or FGH, but not FG something new. So you might ask yourself, well, how would you do that? Well, we can define the update clause differently, right? So the nice thing about the previous update is we can just use this forgetful function. We kind of don't need to do any extra work. There's some sort of automation built in. But instead, if we go back to this point where we're defining the there2 case, we could ask for exactly what the goal type has. So if you look at the goal type, it's fin update to rows A, right? So we can, in the there2 case of uppercase updateR, on the bottommost right-hand side, we're going to just say, if you want to update, then just give me exactly what the goal is, a function from fin update to rows A, but I'm going to give you access to what was already there, the function from fin n to rows A. And then to fill in this goal, we just call the g, which is the extra argument that the update r gave us, and pass in the f, which is the old infinitary argument. And now visually, if we wanted to add an h here, then we can do that by saying there2 here, changing the branching factor to 3, and then having this patch element that will snock on a leaf of h's to the existing rows tree x's, and now we can create this. So basically, what I've shown now is how to perform updates on data types that include dependencies and infinitary arguments. And for the infinitary argument, or for the dependency case, you have sort of choices of how you want to handle this awkwardness of once you update some argument to a data type that is used dependently later on, you somehow need to mediate the transformation to the untouched part. And you can do that either through forgetful functions, or you can just ask for a new value anyway, but give the user the old value to sort of update themselves, or you can pick other ways to do that. And in the actual paper, like I mentioned at the beginning, there are all these other features, and in particular, I advise you to look at it because it contains a really cool construction that was too complicated to show in a brief time slot like this of a dependently typed universe that is defined as an inductive recursive, inductive recursive, inductive, inductive type. And it's pretty cool because it allows you to do generic programming of something like update over any data type definable with dependent arguments, infinitary arguments, and induction recursion. And over a closed universe of types. And yeah, I recommend checking it out. And I'm pretty happy, but I didn't want to present it here because it gets pretty gnarly. Yeah, that's it.
So one of the things that I think the dependently typed programming community has been very good at is talking about all of the fancy exotic ways that we can represent data types, but we have not been good enough at saying what to do with these data types once we've got them. So one of the things I really like in this paper is that we have some, what can I say, concrete advice for how to actually go about doing things with these data types now that we've got our hands on them. So thanks for contributing that, because I think that if you've wanted to learn these things in the past, you had to be essentially at a university where these things were all known to everybody. And getting that on paper is a very nice contribution, in addition to the incredibly gnarly but very cool construction of the universe at the end, which shows how to do all this generically. That said, I think that there's not an explicit list of, what can I say, dogmas for how to write these functions. If you were to come up with such a list, what would you say?
Yeah. So one thing is, at least for the infinitary, for the dependent arguments case, kind of what I mentioned is, you have this weirdness of writing a generic function over a data type that includes a dependency needs to somehow handle the fact that you are changing not only that argument, but the rest of the arguments that might depend on the argument that you're changing in their types. And for that, you always need to sort of choose some sort of way to mediate that, whether, and two examples were presented here. The other thing I would say is, for the infinitary case, you pretty much always need to replicate the infinitary arguments either as other infinitary arguments if you're defining algebraic data types, or as pi types if you're defining recursively defined pi types if you're defining computational data types. And then finally, for the inductive recursive case, which I wasn't able to talk about, it's sort of, it's in a sense halfway a special case with the defining a function over a dependent type or a dependent argument. And then the part that it's not halfway, but the part that it's sort of something extra, is you need to all of a sudden define a lot more functions mutually, because in essence all inductive recursion is doing is sort of adding more mutual definitions, right? You not only have the data type, but you have this interpretation function. So yeah, that would be sort of the three sort of guidelines I would say. But I will admit that there's definitely room for making those more concrete and having more examples, because there's just not a lot of, like I said before, when you look at the literature on doing generic programming, everyone always says like, oh, well, we're going to use this like fancy like type indexed, Dibyer-Setzer universe of inductive recursive types, but then we're going to restrict that universe to first order types and kind of deal with that. So I kind of wanted to say like, okay, what can we actually program with those data types? Yeah.
So it's very nice to have a universe encoding, but that isn't always a practical way to write an actual program, because sometimes it'll be slow to type check or slow to run or difficult to reason about performance, these kind of things. Mm-hmm. Is there something that our programming languages could do that would make this better that you can think of?
Yeah. So there's been a lot of literature previously about sort of the idea of having this kind of beautiful universe that you can elaborate a high-level programming language into, but the problem is during type checking you need to actually perform evaluation, because this is a dependently typed language, and when you're performing evaluation to all this elaborated data, it can be really slow, and you have to be very careful in your implementation to avoid that. And what you can end up doing is instead having these higher level features sort of extend the semantics of your language, but sort of off to the side have the pen and paper proofs of performing the elaboration. Or if you wanted to, you could also elaborate in some like writer monad and check that off to the side or something. But in general, for practical programming languages, I don't advise actually doing the elaborations, and I recommend sort of taking the approach of having a semantics for your higher level features. Otherwise, you can end up with a 20-line program that turns into a 50,000-line program, and that actually happens.
And then, is there a particular application that you've had for this, given that you have these specific examples of lookup and update? Is there something that you want to use these for that's...
Yeah, so kind of something that I've always wanted is sort of a internal language to perform tactics with. So, using dependent types and reflection sort of on these universe codes to write tactics. And the idea here that I ran into when sort of trying to formalize such a thing is your context-independently typed language contain dependencies, and arguments are represented as these higher order things, pi types, and values of pi types are lambdas. So you end up needing this technology in order to manipulate telescopes of data types. So that was kind of the real motivation, concretely, is to try to write tactics within a dependently typed language.
Thanks. I'll hand over to the audience.
Have you considered using this update function concretely to somehow work with balanced trees? How this performs in Actor?
How it performs? I haven't measured performance. No. It's so I have done some initial versions in, like, I had this language that actually performed these elaborations, but it ended up being just incredibly slow, way too slow. And right now I'm working on a new language that does what I was saying before, where we have higher level features that sort of extend the semantics directly. And I expect that to be much better, but I haven't actually, I mean, that's not finished. I don't have performance numbers on that. But
what is the reason for making it slow?
So a lot of it has to do with the idea of taking a high-level pattern matching syntax and turning it into eliminations. And the problem is not the problem in the eliminations is the motives. Like, you end up with these really big motives that constrain your arguments with a bunch of equalities, and that sort of eats away at your memory. And sometimes there's a lot of duplication that you can get away with or remove with memoization and hash consing. But in practice, even doing that in an implementation of a dependently typed language is really difficult, because you usually have to generate fresh names all the time. So all of a sudden you can't memorize anything. So there's one sort of software engineering reason. But even if you would solve those software engineering problems, you still would end up with a whole bunch of motives that are still unique, because they extend across, like, as you're going through a higher order, going underneath a higher order piece of data, you have to extend the context. And so any motives in the extended context will be a different lambda term, because they'll have like an extra argument. So there's a lot of things that are not just duplicated terms. And then when your semantics performs type checking, it has to evaluate all these things. It has to like crawl over all these data structures, which are like enormous. So yeah, that's basically why it's a bad idea, in my opinion, to actually do elaboration in an implementation.
Okay, thank you very much.